Have you ever stopped to think about the invisible science that literally holds our world together? I mean, the incredible forces battling it out inside a tiny ball bearing, or the immense stress on a single column holding up a skyscraper. For engineers, making sure these things don't break isn't just a job, it's a total obsession. So how on earth do they predict the future of a part without just waiting around for it to fail? Well, let's dive in.
Okay, imagine this is your task. You've got this little ball bearing, and it absolutely has to spin perfectly, under load, 500 million times. You can't just put it in a machine and check back in 30 years to see if it's still working. The time it would take, the cost, it's just not possible. So what do? This one question really cuts to the core of a huge challenge in modern engineering.
For a really long time, the only way to find a part's breaking point was, well, you had to break it. It's called physical testing. But as you can probably guess, that whole approach has some massive limitations. It's destructive, for one. It's also incredibly slow and unbelievably expensive. I mean, you can't just build a dozen brand new jet engines just to see how they might fail. There has to be a smarter way to do this.
And that smarter way is to just move the entire test lab, not to a new building, but into the virtual world. Instead of making a physical thing to test, engineers build a perfect digital copy. And that copy, you can stress it, bend it, heat it up, and run it for 1 billion cycles, all inside a computer without ever breaking a single real-world part. This is the big idea right here, the digital twin, and it's truly revolutionary. Now, this isn't just some 3D drawing. It's a super high-fidelity virtual model that behaves just like the real thing because it understands physics. It's got the same material properties, the exact same shape, and it reacts to virtual forces just like the physical object would. It's pretty much the ultimate crash test dummy.
So how do they actually create one of these digital twins? Well, it's basically a 4-step process. First up, you have to create a super precise 3D model using software like SolidWorks. Then step 2, you apply the physics. You tell it what it's made of, like steel or some fancy composite, and what kind of forces it's going to face. Step 3, you run the whole thing through powerful simulation software like ANSYS. And finally, you analyze all that data to predict how it will behave in the real world.
Okay, so what's really happening inside that simulation software? This is where we get to peek inside the virtual test lab and see where the real magic happens and why this approach is such a game changer.
You know, the difference between the old way and the new way is just night and day. Physical testing destroys the part and gives you exactly one data point. Virtual simulation, on the other hand, is totally non-destructive and you can run it thousands of times in a single afternoon. You can tweak the temperature, crank up the load, simulate 20 years of wear and tear, all with just a few clicks. The sheer amount of data you can get is on a whole other level.
So how in the world does the computer pull off these digital miracles? Well, the workhorse technology here is something called finite element analysis, or FEA, and this quote just explains it perfectly. The software takes a super complex object and basically smashes it into millions of tiny, simple shapes. Think of it like a mesh of virtual Legos. It then calculates all the forces on every single one of those little blocks before putting the whole picture back together. It's an unbelievably powerful way to understand stress.
And the range of what you can simulate is just staggering. Seriously, we're talking about everything from the deep internal stresses and fatigue damage on a piece of metal, all the way to the specific vibration signatures of a bearing that has a tiny microscopic flaw. Engineers can simulate how lubricants are going to flow, how a building will hold up in a fire, or even how it might react to an explosion. It's a complete virtual checkup.
The applications are just fascinating. For instance, engineers can quite literally listen to the sound a digital part makes to find potential flaws before it's even built, all by analyzing its simulated vibration signals.
Or they can model the incredibly complex dance of oil inside a high-speed bearing. Doing this ensures every single critical surface stays properly lubricated, which is key to preventing a catastrophic failure years down the line.
And hey, these simulations aren't just for tiny components. Engineers can model how fire will impact the structural integrity of an entire building, making sure safety standards are met without ever having to burn down a test structure.
So here's the really crucial point. This technology moves engineering from just reacting to problems to actively predicting them. It turns all that simulation data into a kind of diagnosis, giving us a little peek into the future life of a component.
And that predictive power is just immense. With these models, engineers can accurately figure out the remaining useful life, or RUL, of a part. That's so critical for knowing exactly when to do maintenance for maximum safety and efficiency. They can perfect designs for strength,
check integrity under the most extreme conditions, and even predict the long-term effects of things like rust and wear. It's all about designing for a full life cycle, not just for day one.
But of course, this field is not standing still. The digital twin is constantly evolving, getting more powerful, more intelligent. So what's the next frontier for this engineering crystal ball?
It's really wild to think about how far this technology has come. From those basic computer models back in the 70s, we moved on to way more complex simulations in the 2000s, and now we've got these incredible high-fidelity digital twins. So the clear next step? Fully integrating artificial intelligence and deep learning. Now this is where things get really exciting. Engineers are now training AI algorithms on the mountains of data that these simulations create. They're using models like convolutional neural networks, which are amazing at spotting hidden patterns, and LSTMs, which are great at understanding how data changes over time. Basically, the AI learns from the simulation, which leads to predictive models that are smarter, faster, and can even correct themselves. They're building a digital twin that doesn't just simulate, it learns.
And all of this brings us to one last really powerful thought. This tech is fundamentally changing what's possible because it takes so much of the guesswork and uncertainty out of design. It lets us build things that are lighter, stronger, and more reliable than we ever could before. So the ultimate question this whole virtual test lab leaves us with is this: if we can perfectly predict the future of our machines, what incredible new things will we be inspired to build next?